Good evening, and thank you for coming for this new A talk, where we have the high pleasure of welcoming Jun Tani, Professor Jun Tani from KAIST in Korea. Professor Jun Tani has a long career in research in robotics, neural networks. He has worked in particular, among other places, at Sony Computer Science Lab in Tokyo. Tonight he's going to talk about how to build hierarchies of more and more abstract representations of the sensory motor experience of robots, which is a core element of today's research on these matters in this field. And I'm extremely pleased to welcome you, Professor, to give us a talk about this topic. Thank you very much.
Yeah, thank you very much. Thank you very much. So I'm very happy to be here, and yeah, I like this atmosphere very much because it's quite, reminds me of my old days of a Sony laboratory. Sony also wants to build like what you are doing, home-like robots starting from eyeball and humanoid robots. But unfortunately, they decide not to continue. But you are now doing after 10 years, and I hope that this time is really, home robots, humanoid robots is appear in real market. So yeah. So anyway, my research motivation has been that try to understand how the higher order abstract knowledge of the world can be acquired by iterative behavior level sensory motor interaction. So in order to for this purpose, so we have conducted something called synthetic neuro-robotics experiments using different type of robots, navigation robots and eyeball and Curio, and now I'm using ear robots also. Today specifically, I'm going to talk about functional hierarchy, how this kind of things can be developed, and then. Of course, so we know that, for example, our brains, so we're going to use for the visual, there is something called visual hierarchy. So that is a very lower level is a V1 and V2. That's a kind of edge detection and a color segmentation, those things. But as a level goes up, and the inferior parietal lobe, inferior temporal lobe is going to be recognize complex shape like face or object, those things. So it's abstraction goes up, and then so that's kind of so that's the visual hierarchy. And also we know that the motor behavior, it's hierarchically organized. In the very top is the prefrontal cortex, and the prefrontal cortex is kind of executive control. It's a global plan, and it sends to the supplementary motor or premotor cortex. It's kind of subroutine level. And M1 is the exact motor profile generated, and it goes upon the spinal cord, and that's actually, it's a motor commands and sent to the muscle, and the muscle generates your desired behavior. But the point is that both of them, so we know that it looks like hierarchy exists. So then, and the question here is that how can the functional hierarchy required for the compositional manipulation of the image or behavior and thoughts be achieved in the artificial as well as biological brain? And then the question is, does such functional hierarchy require symbolical representation or manipulation, as like conventional AI researchers have explored? So that is one question. If so, then how can such symbol, the arbitrary shape of the token, can be grounded in the real sensor motor reality? So that is a long time question. So actually question is that, so the question is, the specific question is, does compositionality require symbol representation or manipulation? If so, what is the reality of the symbols in our heads, that's the brain? Do we really use those symbols? And how can symbols as an arbitrary shape of a token be grounded? That is I already talks. So that this is coming to the problem, symbol grounding problems. That is okay. Stephen Hannard once asked that how the symbolic process in higher cognition can have a a more smooth interaction, natural interaction with the sensory motor level things in the physical world. And what he suggested is that if we provide nice categorizer in terms of software computing like neural network or fuzzy logic, and then symbolical system might be able to interact with sensory motor things. However, crucial difficulty is that these two distinct existence of the symbol not define the metric space, and sensory motor things, it is defined metric space like a length and time and those things, but those are living in a totally different space. How they can interact, that is a crucial question. So then what I have proposed is that higher order cognition might be embedded in a continuous analog dynamical system, which is defined in some metric space. Then it would be able to interact with the physical world because now they share the metric space. So it's like we may have kind of a top-down process of predicting or expecting from the higher level, and then we have a kind of a bottom-up recognition, bottom-up process of recognition of perceptual reality of acting in the world, and then those things exist. And then, so important thing is that in a conflictive situation, these two may not agree. So that and what you expect is really could be different from the perceptual reality. But in that case, so one side push a little bit forward, and the other side may pull back elastically. Then so that point of the compromise might be found dynamically. So that is if you once define the things in the metric space for the higher cognition, that's kind of interaction is possible, dense interaction possible. And then what we can expect is that through the kind of mutual interaction between two sides, subjective mind, the objective world, and then compositionality might be developed, self-organized. So that is a scenario that we have considered. So, and then today's content is something following this kind of thought. And first I'm going to talk about the developmental learning of compositional action by the humanoid robots, especially focusing on the problem of self-organization of functional hierarchy to achieve compositional cognitive mind. And the second one is going to, so it's rather recent my research results about recognizing dynamic visual image pattern through the learning. So again, we're going to look at the functional hierarchy, but this time is that we look at the self-organization of spatial temporal hierarchy from pixel level. So this has been a long time problem in the machine learning vision, but probably this is our proposal first time to deal with dynamic vision through the self-organization. So, and if we have time, so I'm going to talk a little bit about how the action concepts can be acquired in associative learning between the language and action. So that is So first I'm going to talk about developmental learning of a compositional action by the humanoid robots. And the idea is something like that. So what we want to realize is something like we have an intention for acting in the physical world. So we have various intention, like sometimes we want to grasp something, or sometimes you want to hug a person, or many things. But anyway, so the intent, for example, some intention is given, intention 1, then it's going to predict kind of primitive behavior A followed by B and C. That's a primitive behavior, something like grasp, approaching a hand to something and grasp and move up, down, or something like that. Those primitive. And then that one is mapped to the actual pattern and concatenated, and the sensory motor sequence can be generated. So. And then for the different intention, like intention 2, it could be the different way of combining, concatenating the primitive, and thus it's going to be generated different sensory motor sequence. So that is a top-down generation. But it's also you can do the recognition with using the same system. That is starting from the perceptual reality of this one. And then it can be recognized as segmented into the primitive B followed by primitive A. Therefore, it can recognize this is intention 2. So the other way around. So this is a kind of what we call a predictive coding schema and applied to the hierarchical things for the recognition or generation of compositional action. But the question here is that this is kind of a system consisting of a set of symbols, the pointer, and but that is how we can realize this kind of things without using symbols in order to avoid the problem of a symbol grounding problem. So then for this purpose, so we propose so-called multiple timescale recurrent neural network. So that's kind of a neural network, but a very abstract one. But this is have a kind of consists of a different timescale dynamic network. And for example, this case is that this part is a slow dynamics network. This is a fast dynamics network characterized by the large time constant tau. This one is characterized by small time constant tau. So what is a tau? So maybe, I don't know how much you know, but if you think about neural activation, maybe describe the kind of this kind of leaky integrator equation. And then this is each neuron activity described. So, and then if the tau is large, that is the changing of the activity is very slow. So like a mass, big mass is going to be slow. But the mass is very small. A little bit synaptic change is going to a rapidly changing activity. So therefore, tau is small. It's a dominant dynamics because much first. So that's kind of two different type of things. We're going to concatenating the network. And this network is going to learn about perceptual sequence. So that is, and it's going to be done by the supervised manner. So this might be the target sequence, perceptual sequence is corresponding to some kind of a robot behavior. But this is, and then it consists of a kind of a primitive, set of the primitives concatenated. So, and then it is shown to this network, and then this network have to learn to regenerate these things. So this pattern. So in order to do that, we have so-called intention here. So it's a particular intention is provided, then it's going to generate its forward dynamics, and it's going to try to regenerate these things. So similar one is coming. So in terms of dynamics, and then but there is some kind of error exists. So and then therefore its error propagates, and then in the synaptic weight, connectivity weight is changed here, and it's going to change also intention here in the direction of minimizing the error. So, and for the different target sequence which network have to run also, so this is second sequence network have to run, then it starts from a different intention state, initial state, intention state, and it's going to be try to mimic this one, but it still have some kind of the error again propagates and changing weight, and then changing this intention state to the different value. So here, what network have to do is two things. One is try to find connectivity weight, synaptic weights of a neural network that can learn all different sequences. The other thing is that you have to find optimal intention. That is actually key for each sequence. So each different sequence, you need a different key. So that is small vector things that you have to identify. So that's the two things is a learning. This is actually EM algorithm, similar to EM algorithm, if you're familiar with it. And then after many different sequence of the training, and what we expect is that the fast dynamics part may start to run about a set of the primitive appearing many times here. So here, so primitive things. And then slow dynamics might be try to concatenate this. That is a slowly changing profile starting from a particular initial state, that is the intention. That is a slowly changing profile appear here. And it's going to be interact with this first dynamics level, and then it's going to regenerate this combination. So this one is kind of combining signal, these primitive to this way, and the first sequence is regenerated. But if you start from different initial states, so it's a different way of the wave is profile appear, and it's going to interact differently. Therefore, it's going to the different concatenated sequences generated. So this is a kind of compositional generation of behavior, but without using any symbol or pointer. But everything is analog dynamical system, especially for this part is this signal is plays a role of bifurcation. So this value is changing, therefore primitive is going to change, switched. So, and here is that using so-called initial sensitivity characteristic, different initial states, therefore different scenario of the behavior generated. So that's kind of a dynamical systems approach is utilized. So this is the actual network that used for the humanoid robot experiments. So that is consists of the higher level, middle level, time constant is 70 here 5, and the input output level. So that is, this one is a kind of motor module that is actually getting current angle, joint angle, and predict how it will change next time. This part is a vision module. It's going to receiving visual feature, but in this case of 6 years ago, the experiment, that's very small feature, like this robot is going to manipulating object, and the object has a red point, and visually recognize the position. So then XY position, something like that. But that is going to get predict how the visual retinotopic position of the visual objects change in time. So that is going to predict. So that is the given for some intentional state, for example, in a grasping object, and visual proprioceptive sequence is predicted. That is a top-down pathway. So, and also you can operate this in a so-called closed loop. That is, so in order to the kind of mental simulation, so that is this network is receiving the current inputs not from the outside, but your own previous time prediction is fed into this input. So therefore, your prediction is next time becomes input. So therefore, without having external inputs, but the mentally simulate. So depends on the intentional state. You can rehearse so many different way of acting based on pre-round knowledge. That is possible. So, and that might be corresponds to brain science. That is, so we're going to consider like prefrontal might be much slow time scale. This is a rate coding level, and readiness potential goes up, taking several seconds in many cases. But this is the motor cortex of M1. This part is going to be a split of a second. So time scale is quite different. So then what we're going to consider is that, so prefrontal cortex might set some kind of initial state for the supplementary motor area, then slowly changing profile appeared here. That is propagated to the inferior parietal lobe, and it's going to predict exact visual sequence to the V1. And also, it's going to predict how the posture change in time. That the joint angle thing is changing, and it's sent to the motor cortex, and the torque is computed. So that's kind of analogy. How much is true is a discussion, but is we are considering. And if we got kind of prediction error, for example, here visually we predict something, but the reality changes, and then you might get the error. But the error is propagated back to the brain, the IPL and SML, and it's going to modify this initial state, intention state, so as to minimizing the error. So that is an error in the unexpected event. You're going to change your mind, intention change. So that is adaptation to the real world things. Okay. So we use the Sony robots and Curio, and then we're going to choose as a robot so a set of goal-directed action. And in this case, that we choose three different tasks. So that task one, the object is located in front of the robot in a different position, it could be. And it's in a task one sequence, and in the robot approach this one and moving up and down 4 times. After that, moving left and right 4 times, the back and the place back to the in front of you and back to home position. This is very stupid things, but it's so we did something like that. Task 1, task 2 is a different combination of the primitive. It starts from same home position, but the primitive is a different way. So moving forward, backward 4 times, and touch by each hand 4 times back to home position. The task 3 sequence is a different primitive combination. So we choose this in a developmental manner. That is, we teach a little bit. So in the case of tutoring, that is actually we are physically grasping robot hand how to do it. We teach it. So in each task sequence. And we teach a little bit, and then look at how robot behave. So let him do it. If it's not working so well, I'm going to grasp his hand again and teach it. Until he can master these tasks, so that we continue to teach. So, and I'm going to show kind of a developmental pathway, how the robot actually developed the skill. So this is a very fast tutoring. So he is coming to grasp it, and he's supposed to move up, but his control is not good, so he is going to lose. And once he lost, his hand is frozen there. And then this situation, we tested. But he cannot do the physical work because the box is drop off. So, but how much he can do mentally? So we ask a robot kind of mental simulation by closed loop. And actually, we ask a robot to the pantomime. But in that case, robot can actually very first stage of learning, but he already do is kind of a mentally simulating moving up and down. So, but this is control is not good. But he's mentally imaging the objects move up. Visual image is kind of making himself. Therefore, his hand continues to move. But the previous time, once objects drop, then his hand cannot move up because visual objects never go up physically, right? So that's kind of things happen. So, and one in Linda Smith, in a development psychologist, told me that infant development also like that. So that is, it's considered that the mental image developed first and followed by the actual behavior. So, and then so we're gonna do the tutoring a little bit and more. So when we're gonna teach, so and then he's almost okay. So I don't force so much. So his hand is approaching nicely to the object, but here, because he didn't squeeze inside, therefore the object dropped. So therefore I'm asking him to much squeeze. So, but this case, but he resisted. So I can feel his resistance force, but still you have to do this. So I can feel his willingness through the kind of a force. But anyway, but that force is becoming actually error and propagates through his hand to the head, and the back propagation through time, and then and learning goes through. So and once once he can grasp it and he can move up and down by himself. So I'm not doing like this. He is doing. So this is kind of collaboratively training through the physical interaction. Therefore, tutoring trajectory is going to change as time goes by. But we collaboratively finding the nice trajectory for tutoring the robot. That happens. So after second tutoring, what we got is, so it's almost nice. So he can grasp an object and then do that. But sometimes he lost it. So in this time, he can almost okay the moving up and 4 times, but he cannot switch by himself. So moving left and right. After that, he have to switch. Therefore, I provided the cue. So I do like this. So then robot. So I might show that part. So then I do this. Then he understands he has to move to the left and right. So So what we can understand here is that so primitive level, that is moving up or approaching and moving left and right, those things are already okay. However, robot higher level is immature. That is concatenating one primitive to the another. That part is robot cannot do that by himself. After third tutoring, what we got is so this is a slow neuron, slowly changing neuron. This is a fast dynamics neuron. So after 4 times moving up, and he can do moving left, right 4 times and back to the home position. So if you start from different initial state, intention state, this is a third task sequence. So this is slow dynamics part is actually counting how many times I touch it. 3 times he's counting, and then predicting. Now next is a rotating object. It's quite contextual things is encoded in this slow dynamics part. So if we look at developmental pathway, so that is a kind of looking at the task 1 sequence, and after session 1, this is a teaching signal, and this is mental imagery. And the mental imagery, this part is okay, but the second part of primitive is not generated. Actual action generation is completely wrong. He cannot do anything. So, but the section 2 is that now mental imagery is almost okay compared to the tutored one, but the actual action, he cannot switch to the second primitive. He's doing only primitive 1. So, and after session 3, what he can do is that both mental imagery and actual one is going to be very good. So, and also, please look at this. This teaching trajectory, initially it's kind of very not periodic, so much good, not so good, but as time goes by, it's becomes more periodic. That is because the generated one becomes much more periodic. So that is kind of a, yes, collaboration between the robot. So, and the task 1, task 2, task 3, so if you look at this one, and starting from different initial states, and therefore different profiles appear, and therefore different combinations generated. The important thing is here is slowly changing. This one is continuous, very continuous. It's not stepwise changing in case of a primitive 1 to primitive switch. So that is a kind of in order to generate fluid continuous pattern generation. So it's a kind of kinetic melody, and then that's kind of a slowly changing profile is not discrete change. It's kind of continuous change. That is generating a very fluid generation of the behavior as possible. So now I'm coming to the 5 minutes. It's okay. So recognizing dynamic visual image pattern. So that's aiming to achieve semantic level understanding of dynamic visual image through the iterative learning of pixel level perceptual flow. So applying constraints of multiple spatial temporal scale processing to dynamic neural networks. That is kind of, the previous one is we utilize multiple time scale. But now we apply same network with multiple spatial scale. So, and applying both scale things, temporal and scale, we hope that the spatial temporal hierarchy might be get self-organized. And we did it in a visual recognition of compositional human action. So this is the architecture. So that is this is coming video frame input come as a sequence. And this is kind of output part of the action category recognition results comes out as a winner take all part like. And this is a target teaching part. So this is a teaching, this action category or this teaching category depends on video frame sequence. Okay, and this part is the fast dynamics part, and then consisting of a fast unit and allowing only local distance connection. But higher level is might be a much more global one, and slow dynamics unit is allocated. So that is higher level is a slow dynamics and larger long distance connection. But the lower level is a fast dynamics unit and only narrow connection. Receptive field changing in the lower level much narrow, but higher level is much more global. So that's kind of constraints. But so we're going to show the results and skipping. So this is what we did. The experiment is that so we use a video image for the Weitzman data set, and then one is so this is jumping in a place video, and then we use wave one hand, wave two hand. So and then what we did is making a testing sequence that is concatenated. So it's first is jumping, next one is jumping, and the blackout signal comes, and the network have to answer which one. So then next one is the first jumping, and the next one is a waving hand, and then blackout comes and answer it. So answer is always delay response manner. So that is network have to answer it. So I'm gonna show the video of this one. So this is the first jumping, and the second one is jumping, and now answer. So this is category 1, jumping, followed by the one hand. So this is category 2. So combination of the action sequence is recognized. So this is a pixel level. This is a fast dynamics, middle, and slow. So it's, you see that this is changing very slow and recognizing. So. And this is only delay response after blackout, and the answer comes out. So that's kind of dynamics is learned. So and what you can see is something like so it's this is kind of in a different subjects case. Subject 1, subject 2, subject 3 are all subject different way of jumping, or one hand waving. So this case is jumping. But subject 1, subject 2, subject 3, so this is kind of fast dynamics part is quite different. However, if you look at the slow dynamics part, this is many neuron, but its profile is quite similar. Therefore, could be able to categorize. So that's kind of generalization among different subjects is possible. If you look at this one, one hand waving followed by jumping. This is a two-hand waving followed by jumping. So this part of the jumping is the same. However, you look at the slow dynamics part. So this encoding is quite different, even though doing same thing. Why different? Because it's carrying a context. The first premise is a one hand moving. This is a two hand moving. So that difference is coming. So therefore, network can recognize. So now we are working something like raw data of using and the object, different object, and the different combinations. Those things we are doing. So. Okay, so I am almost coming to the summary. So I skipped this language part. So important things is this one. So that is so cognitive mind emerges through the reciprocal interaction. That is we have top-down things and the bottom-up things and reciprocally interacting, and then some structure of compositionality appears. So and also today I cannot show anything but a linguistic part. And also this is using analog dynamical system, and the behavior generation part, analog dynamical system. That is kind of a robot understand what human saying, and then generating corresponding behavior. But in this case is also we have a linguistic process, and the behavior process is interacting very densely, therefore really grounded language, the grounded really sensory motor level. That kind of thing is possible. So. Okay, so finally, so that is, it reminds me like a Merleau-Ponty. This is because France and philosophy Merleau and the visible and the invisible. But what he's saying is very important. Is that there is reciprocal insertion and the interweaving of one in other. So he's talking about the interaction between subject mind and the environment through the reciprocal interaction. That is quite important. In that case, the subject and the object differentiation is gone. That same thing, the language and the behavior is mutually intact, and the boundary cannot be seen. That time, the language is really grounded to the sensory motor reality. So that's, I think, end.